which is what we're starting today into. I'm going to try and do it in 3 sections. So we'll talk about acid-base chemistry today. We'll look at substitution elimination chemistry on Wednesday. Next Monday will be the redox chemistry. And then next Wednesday will be kind of a review where we put everything together and we look at ultimately the same type of question as question 10, I believe, from quiz 11, okay? The reaction, okay? At that point, we'll have tons of options as far as reactivity goes. So we'll have all of the alcohol reactivity, we'll have the alkene reactivity, and we'll also then have alkyl halides as well as part of that, okay? So lots and lots of chemistry to have at our fingertips to be able to work with. At the end of that chapter. So that's kind of what that Wednesday will be. I'm hoping next Monday will be a recorded lecture. Okay, so we'll post that and then just work on a quiz again in class. Okay, maybe kind of directed a little bit smoother as well. Okay, so with the alkene chemistry, we saw this spider diagram which shows all of the reactions that we know so far about alkenes. You are responsible for all of those reactions. Okay, so you need to know them because you have to be able to recall them and pull them up as far as processing reactions. Is this not what was posted? Should have been what was posted. Right? Okay. Chapter 8, looking at our alcohol homework. So we've got some nomenclature, some physical properties, and then the questions kind of bounce around a little bit. That temporarily skipped thing I need to reevaluate, so ignore that for the moment. I don't remember what those are about. Okay. Chapter 10, amines, we'll look at some amine chemistry. Ultimately, today is where we're going to see it. All we're concerned about with the amines is their acid-base characteristics. Okay, so it's going to be a lot of acid-base chemistry today, and then what we can do with those, and then we'll kind of move on from there. Okay. So, to start off with, I do want to keep coming back to resonance and mechanisms because you're going to keep seeing these. Every test from here on out, and it's only 2 of them, will have at least one mechanism. Complete, beginning to end mechanism. Okay? You can also expect to see intermediate questions where I may say provide just the mechanistic arrows to go from step A to step B. Okay? So it's a little bit easier because it's much more targeted. You don't have to predict the whole thing. Okay? The principles behind mechanisms and the principles behind resonance structures are ultimately the same. You're just moving electrons, and it's a question of how those electrons move, where you're moving them to, that changes what you can do with them. Okay? So it's all about moving the electrons from some place that has them to some place that could be missing them. Okay? So it's always negative to positive. Never, ever, ever move an atom. It may appear that an atom is moving in some cases. Say when a nucleophile attacks an electrophile, and it's not really moving the atom, you're taking the electrons that the nucleophile has and you're sharing them. In the process, you make a bond. Okay, so it's not the atom moving, it's the electrons moving. Okay? When you're looking at resonance, pretty much the only electrons you can touch are lone pairs and pi bonds. Okay, which, yeah, they are up there. Okay, right up at the very top. Those are the only ones that you can deal with. And when you go through and deal with resonance, what you're going to be shifting around are either lone pairs and pi bonds. If a sigma bond changes, you no longer have a resonance structure. Okay, then you're moving into a mechanism. So if you're asked to draw resonance, make sure your sigma structure stays the same. Okay? No sigma bonds breaking. Okay? You can shift those electrons in very particular fashions from atom to bond and bond to atom. Okay? You'll notice that I left one kind of rule off on that. What's the last rule on how you can move electrons? Anybody know? Really, it's just the shortcut of A and B. I can move electrons from an atom or from a bond to an atom, and then from that atom to a new bond, which means ultimately I can say, instead of doing all of that, I can say bond to bond. These are proximal locations, so you're only moving it to the atom immediately next to it or the bond immediately next to it. You cannot jump through a structure. Why can't you jump through a structure? Electrons are point charges, extremely unstable. They cannot move through space. Okay? So we have to move them immediately next to something that can hold on to them or stabilize them. Okay? If your octet's not satisfied, that's when you can go through and start shifting pi bonds. Okay? If you've exceeded the octet, but it's all sigma bonds, what happens? Okay, so if we go through, see if I can draw an example here. I want to see if I can do resonance with this negative carbon by pushing the electrons here. How many bonds are around the soon-to-be blue carbon? There's 4 bonds plus the pi bond that's trying to form, okay, which means we've exceeded the octet, so we have to fix that by breaking a pi bond. What's the only pi bond available? The one we just made, so the electrons go right back. What does that mean as far as resonance? I can't do resonance in that direction of the structure. Okay? So it's an important evaluation of that structure. I now can't do resonance through that area. Okay? What does that do to the negative charge? Does it become more negative or less negative if I can't do resonance? It becomes more negative. Okay? Because if I had resonance, I would reduce the negative charge because I'm now spreading it over a larger area. Here I'm saying I can't do resonance. That negative charge is localized. It's at one position. It's going to stay very, very negative. Okay? We get very similar rules when we move into mechanisms, except now in mechanisms, you can make and break sigma bonds. Okay? So it's the one big change. Whenever we're going through and trying to deal with mechanisms, we're always going to make and break the easiest bond possible. Okay? So the first bond we'll jump to would be pi bonds. If we don't have pi bonds, then we'll try and attempt to break sigma bonds. Which of these sigma bonds would be the easiest to break? Carbon hydrogen or carbon chlorine? Probably the carbon chlorine. Why? It's polar. The electron density in that bond is already shifted towards the chloride. Why is it already shifted towards the chloride? Because chlorine is more electronegative. Okay? So we can evaluate on deciding what bonds are better to make or break in this case by looking at differences in electronegativity. Okay? And it will elevate too. Okay? Questions about resonance and mechanisms? Okay. So those were our general rules. Hopefully as we continue through, we'll look at more specific things. Okay? We're going to do a brief circle around of bonds and forces just to kind of remind you of what's going on with these. Okay? These intermolecular forces and bonds were important to try and predict different reactions. We just looked at deciding which sigma bond was easier to break. Carbon hydrogen versus carbon chlorine. We said the carbon chlorine was easier to break. Why? What type of bond is that? It's a polar covalent bond. Okay? Versus a covalent bond. Okay? As we move further up, we're starting to move closer and closer towards our forces. We're becoming less sharing of electrons, less like a bond. Okay? Which is easier? What kind of bond is easier to break? One that isn't a bond or one that is a bond? Okay? The one that isn't is easier to break because it's already not there. Okay? Phase transitions, solubility, and reactivity. So we just looked at reactivity, evaluating the bonds. Okay? The other two, our phase transitions and solubilities, are ultimately looking at the forces. If I have a compound that has really strong intermolecular forces, how much energy is it going to take to rip that molecule away from other molecules? More or less? More, okay? Because of the strong forces. Okay, what does that mean about the melting point? Higher or lower? Should be higher because it requires more energy to break it away. Okay? So applying this wheel, as goofy as it may seem, can start to predict a lot of the chemistry that you're seeing. Okay? And we can use that to identify ultimately the reactivity, which is really what you're going to be concerned about pretty much for the rest of the semester. Identifying Bronsted-Lowry acids, Lewis acids, electrophiles, and nucleophiles. How do you know you have a Bronsted-Lowry acid? First thing you can tell me. Bronsted means hydrogen. If it's a Bronsted-Lowry acid, what is that hydrogen likely attached to? It should be H+, but if it's not actually shown as H+, something's temporarily stabilizing it. What can you tell me about that something attached to it? Whatever that atom is must be... Anybody? Good call, going off the definitions. Should have a high electronegativity. Why? An acid should be what charge? H+. How do I get it to be plus? Got some species that's taking the electrons away from it. So whatever that atom X is, has to have a high electronegativity. Okay, so what's your favorite acid? HCl. Why is that a good strong acid? What can you tell me about the chloride? It's electronegative. Okay, so looking for those simple patterns, as simple and obvious as they may seem, those simplifications or analyses can help you solve a lot of the chemistry that you might encounter. Okay? So this has a lot of information condensed onto it. So what I'm trying to show here is the intermolecular forces, something about physical properties in orange, and then reactivity underneath. Okay? So we started the semester off in Chapter 3 with our alkanes. Okay? What intermolecular forces would we predict for our alkanes? There's a sheet answer, it's up there. We're looking at our London dispersion forces. Why? What types of bonds do we find in our alkanes? Covalent. Okay? Covalent bonds lead to London dispersion forces. Okay? Since we've got equal sharing of electrons, how strong are those bonds? Or how easy would they be to break? Relatively strong, which means what about its reactivity? Virtually unreactive. Okay? We didn't look at any reactions that could potentially cause an alkane to react. Okay? We don't have that polarity that we need to cause these things to shift. Okay? The next thing we moved to was looking at your alkyl halides, which everybody loved because that was Chapter 7. Okay? Looking at the alkyl halide reactivities, substitutions, and eliminations. Okay? So we upped the intermolecular force strength because we're introducing that alkyl halide, the halide portion of that. It's electronegative, it's going to draw electron density away. This means the boiling point and melting point should increase over similar alkanes. Why? Because we've introduced that polarity. Okay? That dipole that's now going to require stronger forces to break molecules apart. This also introduces some chemistry for us, and this is where we got the electrophilic carbon. Okay? The halide can't do a whole lot because it can only form one bond. It's already got that bond to the carbon. So what we're looking at is that carbon becoming electrophilic. It wants electrons from somewhere else. Okay, so nice. Pretty much only one type of reaction. We then move to the alkenes, which we finished up last week. Okay, we're looking at stronger London dispersion forces, stronger because we've got that pi bond in between, which causes some polarization, a little bit easier to interact with. So we might predict some higher melting points and boiling points when compared to our alkanes. Okay? And as far as reactivity, what do we end up getting out of our alkenes? What was the reactive part of the alkene? The pi bond. What's in a pi bond? Electrons. Which definition matches electrons best? We get nucleophilic carbons, okay, so something that can donate electron density, say to bromine. Okay. We also had them being able to donate that electron density to say something like hydrogen, where we reacted with our strong acids. So our alkenes could act as two things, a nucleophilic carbon and a Bronsted-Lowry basic carbon. Okay, so two possible sources of reactivity. What we're now going to move into is your alcohols and amines. Okay? Alcohols are particularly irritating for a couple different reasons. Number one, we've got a very strong intermolecular force with our hydrogen bonding, which means our melting points and boiling points skyrocket. Okay? Because we've got that strong force. It's going to require a lot of energy to break those compounds away from like-minded alkanes, okay, or like-weighted alkanes. When we move to the reactivity, this is where it gets even more dangerous. Okay, we get the electrophilic carbon just like we did with the alkyl halides. Okay, we have a very electronegative element in that oxygen pulling electron density away from the carbon. That means that we can supply some electrons towards that carbon in the form of a nucleophile. We could potentially see some substitution reactions. Okay? The other issue, that oxygen starts with lone pairs. So it's already, without having to do anything else to it, nucleophilic. Okay? Because it has those lone pairs. Taken further, it's also already a base. Because again, it has the lone pair electrons to react with it. Okay? Just to make things even more irritating, we also get another positive atom out on the other side with our hydrogen. Okay? Why is the hydrogen reactive? Because it has the electronegative element attached to it, making that hydrogen acidic. Okay? So alcohols are tricky as a functional group because we've got lots of different possible reactions that can occur. Okay, so you need to be aware of all of that chemistry. When we move up to the amines, we still have hydrogen bonding. They aren't quite as strong hydrogen bonding. Why? What? What's special about the nitrogen? Why is it not as strong as the alcohol? Why is it? What do you mean by strong? It's not as electronegative as oxygen, which means the dipole generated isn't as big, which means we get a slightly weaker hydrogen bonding force. Okay? When we compare it back to the alkanes, we would still predict the amines to have a higher boiling point or melting point, but nowhere near as high as the alcohols. Okay? We can go through and evaluate, just like we did before, the reactivity of our amines, but because the electronegativity is changed, we also end up changing some of the chemistry as well. Okay? We do have an electrophilic carbon where the nitrogen is attached. It's a good thing I had that nice and highlighted. Okay, so we've got that carbon in there. We still have a nitrogen with lone pairs. Because of the presence of the lone pairs, we have a nucleophilic nitrogen atom. Okay? With lone pairs, again, we also shift to it being basic. Okay? You'll notice the one big thing missing here, though, is we say we don't have an acidic hydrogen. Okay? Why are those hydrogens not acidic? It's a harder question. Why was the alcohol acidic? Oxygen was more electronegative. What did we say the comparison between nitrogen and oxygen? Nitrogen was less electronegative. So the threshold for that hydrogen to become acidic happens to be substantially higher. Okay? So even though nitrogen is electronegative, it's not electronegative enough to physically rip the electrons away from the hydrogen to have it act as a good acid. Okay? So when we look at amines, it's a little bit nicer because what you would expect of your amines is for them to act primarily as bases. Okay? It's going to be our primary focus with amines. Okay? And that's what Chapter 10 is ultimately all about. Amines act as bases in this case, in this case, in this case, in this case, and some more other cases. Okay? So that's all the chemistry in Chapter 8 and 10. Any questions? Okay, well, that's about all I got, so we got about an hour for questions. No. We'll go through some examples. Okay. So another thing we can go through and do is kind of constantly keep going back to some basics. Okay, we've gone through now 4 different types of reactions: your acid-base chemistry, substitution, elimination, and addition. You should be able to look at an individual reaction and say, I think it's going to do that type of reaction. Okay, pretty close to instantaneously. Within a few seconds, you should be guessing at one of those 4 options. Okay, the one case where I would say you don't have to do that would be if you start with an alcohol functional group. Okay, so remember, the alcohols allow you to do everything. So just looking at that functional group of an alcohol, you're probably not going to be able to predict the reaction right away. Okay? So with these, let's go through and try and identify the changes. What bonds are broken and what bonds are formed. Let's start with the very top. What bond was broken? Okay? We broke a bond between the hydrogen and the oxygen. We break any other bonds? We didn't break any bonds, but we did form a bond. What was that bond that was formed? Between our hydrogen and nitrogen. So what type of reaction happened here? We looked at the transfer of a hydrogen from one atom to another. We're looking at acid-base chemistry. Next reaction. What bonds were broken? Broke our carbon iodine. What bond was formed? Our chlorine iodide, and I already heard people telling me the answer. We're looking at a substitution reaction. Next one. Same idea, bonds broken, bonds formed. And bond formed. Is there another bond broken? Also lost a hydrogen. Okay. So if we look at this reaction, we're looking at an elimination reaction. I don't know if I can fit that all here. Close enough. Last one. A little bit trickier. I tried to make it as generic as possible, so it might be difficult to piece it together. What bonds were broken? Broke the pi bond. And what other bond do we break? Some weird squiggly thing in the middle. I'll address that in a second. What did we form? 2 squiggly weird things on the outside. What type of reaction do we do here? We have an addition reaction. Okay, in an attempt to keep things as generic as possible so you could apply the chemistry across the board, what I've shown here is a delta positive, delta negative. Okay, so we have a partial charge generated with that reagent. That's what ends up reacting with our alkene. What's an example reagent? HBr. HBr. What can you tell me about HBr? It's a strong acid, which means it completely erases in one swipe. We get H plus and Br minus. That seems to fit under the positive-negative rule. Okay. What other type of reagent have we added? HCl. That's going to fall into the exact same format. What other ones? Could try and add bromine, bromine. Don't really see a positive and negative on that one, but how did the reaction work? The alkene attacked the bromine. What charge would the bromine be if the alkene attacked it? Must be positive. we're generating a partial charge in that reaction. As the alkene comes up, it pushes the electron density away from one of those bromines, making it positive, and the other one becomes negative. Okay? So again, being able to identify these reactions, coming up with common patterns between them, can help you predict what things need to be happening, what reagents you should be sliding in different spots. Okay? Questions about that one? Okay. No. Okay. So now what we can do is move to some actual acid-base chemistry. Okay. Alcohols we've already established, or we already kind of summarized, are very flexible reagents, meaning they can do multiple different things. Even within the acid-base category, they can do multiple different things depending on what we react them with. Okay? So alcohols kind of sit in this neutral area where they can go both ways, both an acid or as a base. Why might that be the case? Does an alcohol look particularly familiar? Say, what if I did that? Instead of having a carbon on one side, I add a hydrogen. What functional group or what structure do I have now? Water. What can water act as? An acid or a base. Alcohols are in that same category as water. So anything that you can imagine water to do, alcohols can do just as well. Okay? Their reactivity is virtually identical. Okay? So we can go through individual reactions where I can take an alcohol and add hydroxide. Okay? What's the most reactive species in the reactant there? Okay, in our top. It's the most reactive thing there. How about A or B? B. Why B? We get a negative charge in that oxygen, which means what do we need to find in A? Something positive. What things are positive in A? We've got the hydrogen. What else is positive? We've got the carbon. Okay? So depending on the chemistry that we might be pushing, we might be looking at potentially a substitution reaction if our hydroxide attacked the carbon, or an acid-base reaction if the hydroxide attacks the hydrogen. Okay? We'll look at those individual reactions when they show up as we go. In this case, we'll just focus on it acting as an acid. So what happens? Hey, A and B, acid-base, right? Would have thought I planned it. Okay, if we're going to draw out a mechanism, we want to find our source of electrons, which happens to be which oxygen? B. So we'll show our electrons starting there, and we're going to draw them going towards our hydrogen. Okay, at this point, we're starting our electrons on an atom, driving them towards an atom, which means we are forming a new bond. What type of bond are we forming? Sigma bond. Okay? How many bonds would that hydrogen then have? 2. How many bonds can hydrogen have? 1. So we now must break a bond. Which bond do we break? Okay? We will probably break the bond, the other choice. Okay? We could just as easily break the bond that we were trying to form, except that doesn't take us anywhere, which is why we've got the equilibrium arrow in between. Okay? So it could go either direction. Okay? As a result of that, we now draw where the electrons ended up. Species B shared electrons, which also refers to losing electrons. So if it started negative and loses electrons, it should be starts negative, loses an electron, becomes neutral. So when we look at our product, we should draw that out where our oxygen is now neutral. So we can evaluate it as the electron transfers, or as I'm sure you all did, remember that organic simplification chart at the very beginning of the semester that I said you should absolutely memorize so that you knew exactly how different formal charges were? There was a reason I told you to memorize it, because you could now just look at this and say, oxygen has 2 bonds. its formal charge is neutral. Okay? So there's a reason I tell you to do something. If you don't want to do them, that's entirely up to you. There are other ways around them. Okay? What happens to the other oxygen from our alcohol? Started neutral. It just gained a pair of electrons, so it should now be negative. We have to specify that formal negative charge in our product. Okay, kind of makes sense? Is this too slow? Too fast? Just right? Okay. What happens in the bottom case? That's an eraser. Let's try this in blue this time. We'll go through and look at structure A and B. This time I planned it. What's the most reactive structure, A or B? Okay, since I'm only hearing one answer, we'll stick with that. How about A? Why would A be more reactive? Because it's charged. Okay, what's the charge? Positive on the oxygen. Does oxygen want to be positive? No. So what does it need to do? It needs to take electrons from something. Okay, can we bring electrons outside the structure and give them to oxygen? Okay, to do that, we'd have to share electrons with oxygen. So we'd be adding 2 more electrons to that oxygen. Can oxygen take 2 more electrons? How many electrons are currently around it? 8. If we add 2 more, we're up to 10, which means we exceed the octet rule. Can't do that. So what we have to do is look within that structure for an electron source. Okay, this one's fairly nice because there's not a whole lot else to it. Where are there electrons within that structure? In those bonds. Okay? So what we'll do is take electrons away from one of those hydrogen atoms and put them on the oxygen. That generates what charged species? Fair answer. We generate water, which is neutral, and a positive hydrogen. What do we need to stabilize the positive hydrogen? What do you need to get rid of a positive charge? You need electrons. So now we move to structure B and try and find electrons. Where are there electrons? Try that again, sorry. Maybe a little bit louder. On the oxygen, I don't quite accept that. Lone pairs, where else are there electrons? Bonds, which type of bonds? Sigma bonds. So we're looking at electrons being in the sigma bonds and in the lone pairs. Which of those is more accessible? The lone pairs. So what can we do? We can have the lone pair, or one of the lone pairs on the oxygen from our alcohol share with the hydrogen. You'll notice we go from atom to atom. Okay? We're trying to show where our electrons are physically moving to and from. The result of this, we form a new bond between our oxygen and our hydrogen. Our oxygen started neutral, lost electrons, so it is now positively charged. Okay? Questions about that? Okay, because now we're only going to make it more difficult. I promise. Okay? So let's see if I can wire lift. Yeah, so much for that. Okay, so just as kind of a refresher, what we're going to start to move into is, can we tweak acid-base strength? Okay, so it's helpful if we remember some rules about these. Okay, a stronger acid needs to steal electrons away from a hydrogen. That's ultimately how we get that H+. Okay? To do that, we usually pull the electrons into the structure. Okay, so if we can show resonance where electron density is moving into the structure away from the hydrogen, that species ends up becoming more acidic. Okay, so we're looking at something that's ultimately less negative. Okay, why? If we get rid of H+, what would we be left with if we started with a neutral compound? A negative charge. The less negative it is, the more stable, the more likely or more willing it is to give up that hydrogen ion. Okay? So we can move through some of the rules. How we classified our acids before was looking at the conjugate base. So what we did is set up small mini reactions, pulled off the hydrogen, and evaluated the conjugate base product. Okay? So we looked at size. Okay? The bigger it was, the stronger the acid. HI was a stronger acid than HF because iodine was bigger, even though fluoride's more electronegative. Okay? So size was our primary rule. The next thing we can move to was electronegativity. The more electronegative, the stronger the acid. Okay? Remember, size first, then electronegativity. The other rules we looked at were induction and resonance. Resonance is going to play a major role in looking at these next sequence of problems. Okay? So be aware of that. We're going to see those pop up again. Okay? When we look at our resonance, the more negative our structure becomes, the weaker the acid. Remember, we want something less negative. Okay, the less negative we can build our structure, the stronger the acid. Okay, so it's trying to evaluate those differences and how resonance affects the overall structure. Okay, so we can't go say just more resonance equals better. We have to evaluate how that resonance affects the overall structure. So it's a bit trickier than just saying more or less. When we move over to base strength, okay, a stronger base has too many electrons. So we're looking at something that can give up its electrons to a hydrogen atom. So extra electrons. So those electrons we want to be pushed out of the structure. So if we start with a neutral structure, how can I make it more basic? Do I want to make it more positive or more negative? I want to make it more negative because it needs to react with H+. Okay? So that was, oh no, it's not supposed to be numbered. The stronger base, we're looking at available electrons. So what would be good available electrons? Examples. We're looking at lone pairs and pi bonds. There's an and in there somewhere. Okay? The smaller our atom is, the stronger the base. Why? Let's pick a standard base. This is going to suck for anybody watching the lecture at home. Let's pick F minus versus I minus. Which one's going to be the stronger base? Okay. Well, according to our rules, the smaller it is, the stronger the base. Which one of these is smaller? Fluoride. Why is fluoride a stronger base? Okay. For it to react as a base, the electrons must encounter a hydrogen. If we're going to be a hydrogen and come up and react with either of these, what's the likelihood I'm going to come up and see the electron in fluoride versus the likelihood I come up in that same space and see the electron in iodide? Okay. Fluoride, I've got the electron density trapped in a small area. Iodide over a much larger area. So iodide's not going to act as good of a base. Okay. So it has to do with the electrons. Iodide is effectively less negative. Okay. Next thing we can shift to is resonance. So again, we can look at our charges. The more negative we can put into our structure, or the more negative charges we build on it, likely the stronger the base. The less negative it is, the weaker the base. Okay? Kind of comfortable with those rules? We're about to see some examples, so hopefully it'll help crystallize. Or I could say recrystallize, for those of you that remember the labs. Okay, so acid strength altered. So what we're going to do is take a look at some functional groups. Okay? What functional groups would you call each of these? As a first approximation, we might call them all alcohols. Why do you want to call them alcohols? They're OHs, so we see OHs across the board on these. Okay? So we might go through and say each of these is an alcohol. Turns out we don't call them all alcohols. Why not? Because their acid-base chemistry changes substantially, so much so that we, instead of calling them an alcohol, we give them a new functional group name. Okay? So let's go through and kind of evaluate these. Let's compare the first two. Okay? Which of those would I expect to be the stronger acid? A or B? Okay, for it to be a stronger acid, what were the rules? I already forgot them. What were our rules? Size, electronegativity, and resonance. We could look at induction, but that's going to be a little bit more tricky than we want to. Size. Where's the negative charge held in each of these? So we evaluate our conjugate base. So we could draw out our conjugates. Because I'm going to run out of space, I'm going to have to turn it sideways. Versus the other one. Where's the negative charge? It's on oxygen in both cases. Okay. Is there a difference in size? No. Negative charge is on the same atom. Same atoms are going to have the same size. So we could move to electronegativity. Is there a difference in electronegativity between oxygen and oxygen? No. So now what we've got to do is evaluate resonance. Okay, so let's start with the first one. Can I take these electrons, okay, on that negatively charged oxygen and move them? I only have one way to move them. Nice of me, I picked an example that only had one option. Okay. Can I move them into a double bond there? Okay, to do that, I have to evaluate that carbon and say, do I exceed its octet or not? Okay. I only see 3 bonds, so why can't I form a pi bond? There's a hydrogen on there from the very beginning. Implied hydrogens, the bane of everyone's existence. Okay? Which means if I try and move the electrons in, the only bond, or the thing I have to break would be a pi bond, which is the pi bond I just formed, which means what as far as our resonance? That is a big eraser. We have no resonance. Okay, so that negative charge sits on that oxygen. Let's move to the next problem. What happens when I try and shift the electrons in now? Okay, look at that carbon. I would have 5 bonds. Absolutely true. But do I have an alternate pi bond to break? Yes. I can make that pi bond move to that carbon atom. What does that mean? I can make the carbon negative, but I can take the negative charge on this oxygen, and instead of it sitting only on the oxygen atom, I can distribute it across 3 other carbons. You should draw those resonance structures. Okay? What does that mean? More stable because it has become less overall negative. If the conjugate base is more stable, what does that mean about the acidity of my starting acid? It's a stronger acid. Okay? As quantification, I know at least one person was in 152. Do we have anybody else that was from 152? Really? No one? Okay, no quantification, you just got to accept it. Okay? It's just not going to help if you don't know what I'm talking about. Okay? More than what I'm talking about. So the alcohol in structure B is substantially more acidic. If we look at the scale, I think it's 6,000 times more acidic. Okay? That's a pretty huge difference. Okay? So what does that mean? Instead of calling this an alcohol, what do we end up calling it? Anybody really good with their functional groups? P for... Hey, good call. A phenol. Not phenyl, phenol. I know. Okay? Whereas the first one was an alcohol. So what we've done is tweaked the acidity of the compound by evaluating resonance. Okay? If we now throw structure C into the mix, what do you think about C? So we'll put most, put least. What do you think about C? Anybody propagate out all those resonance structures in their head to decide? That's a bit of a stretch. Go through and draw them, and what you will end up finding is we have one extra resonance structure where we can pull the electron density out to that nitrogen. Okay? One extra resonance structure means more acidic or more stable conjugate base, so we put C further up. Okay? How about D? We'll draw this one out. Because circle means those are all double bonds just kind of moving around in there. We got resonance. And I'm going to be lazy about it. We'll talk about that at the very end of the semester, aromatic rings. Just like with the others, now that we've got our conjugate base, we want to attempt to do a resonance structure. So let's take those electrons and shift them in. How many bonds would that central carbon now have? Too many, so what do I need to do? Break a pi bond. Do I have a pi bond to break? Yes. And shift the electrons up there. So 2 resonance structures versus with each of these other ones. So with our first phenol, I didn't actually tell you the number on that. You should be able to get 3 total resonance. The next one, I think you just get 1 more. So 4 resonance. Oh! Undo that. And this last one, we only get 2 resonance. Being kind of tricky on this one. Anybody memorize their functional groups? Carboxylic acid. Phenol versus a carboxylic acid. Which do you think is more acidic? Probably the acid. Okay. Why is D the most acidic? I didn't leave myself a lot of space, but I didn't want to give away answers. It only has 2 resonance structures versus the 3 and the 4. What are you saying? They all have negative charge in the resonance, so it's not quite that, but it has to do with that negative charge. Where does the negative charge end up in our phenols? It ends on a carbon atom. There's our negative charge on that carbon. Where does it end in the carboxylic acid? Oxygen. Which atom can hold a negative charge better? Oxygen can hold a negative charge better than carbon because oxygen is more electronegative. So it may have less resonance, but the resonance contributors it does have are better than all the ones the other one has. Okay? So we end up generating yet a new acid out of this. Okay? And this is where we get our carboxylic acids. The times, if we approximate, I did the math. Oh, crap. What did I say? 6,000 from the alcohol to the phenol. I think that's right. It's about 12,000 down to the acid from the alcohol. Okay? Anybody challenge those numbers? Okay, good. That's what we'll stick with. And I'm sure I'll get comments online saying, you're wrong. But it's close enough. It's a big difference. That's all we really need to hear. Okay? So looking at those resonance contributors can start to change what we would predict for that simple functional group, our OH bond. Okay? And that's ultimately what I want you guys to get at and to be able to see. Okay? So a big part of this next test, particularly when it comes to alcohols, is going to be everybody's favorite 9-letter word, resonance. Not 7 letters. Not since the last time I counted. Okay? So can we further alter the acid-base characteristics? So So we looked at resonance. How about we switch out a functional group? Instead of it being an oxygen, let's make it a nitrogen. Okay? So what happens when we change it to a nitrogen? So let's go through and evaluate. Okay? We still have the lone pair of electrons. Okay? So that's ultimately the same between oxygen and nitrogen. We really don't only care about one of those pairs. Why do we not care about the second one? How many pairs of electrons can you move at any given instant? One. Okay, so as long as you got one, that's all you need to compare. Okay? We can then go through and look at the hydrogen. The hydrogen is on an electronegative element in both cases. So we might predict that our amine would act very similarly to the alcohols. And I walk too far away. Yep. Okay, so we walk all the way back, and we end up finding out that we don't get that acidity. Okay? And unfortunately, there's not a really good answer that I can give to you other than it just doesn't work. Okay? That nitrogen can't stabilize the conjugate base. Okay? So if we tried to remove the hydrogen from that structure, put the electrons on the nitrogen, we get what can be called an amide. The nitrogen's not the greatest at stabilizing that negative charge, which ultimately comes back to electronegativity and resonance. True, but there's a better answer. How do we stabilize charge? You got me saying it now. Electronegativity and size. Nitrogen's not that big, okay, and it doesn't have the electronegativity to overcome that difference. Okay? So what we end up finding out is that nitrogens don't act very well as acids. That gets rid of the acid part of it. That still leaves us with the base part. We still have that lone pair. So when we look at amine functional groups, what you need to be thinking about is they act as bases. Okay? So what we're primarily concerned about is how that nitrogen can share its lone pairs. Okay? So we'll switch colors now because we're no longer acidic, right? Okay, so let's compare these two. Which of these might we expect to be more basic? Okay, far right. Good thing I drew on all those lone pairs. Okay, so the first thing we want to do if we're trying to find out if it can act as a base is see if we can dump those electrons into the structure. If the electrons move into the structure, what does that do as far as the reactivity or the basicity of that nitrogen? Makes it more stable, which means it is more stable means less reactive. Okay? Because we're looking at a different situation here. Okay? When you did the more stable, more reactive, you were looking across a reaction area. You said a more stable base was a stronger acid. Here we're not looking at that. We're looking at evaluating the base strength. If I can take that lone pair and I can move it into the structure, where is it not going? It's not being shared with H+. Well, if it doesn't share with H+, what does that mean about it being acting as a base? Not a base. It didn't react with H+. Okay? So, let's evaluate. Do we have this resonance structure? Can I move those electrons into forming a pi bond on structure A? Why not? Okay. We do have an extra hydrogen there. That central carbon would have too many bonds, so we'd have to move a pi bond if we're dealing with resonance. The only pi bond we've got is the one we just made, which means it goes right back to the nitrogen, and we have no extra structures. Okay, we're only looking at one structure for that. What happens in the case of B? So we'll try and do the exact same thing. Let's move the electrons down into the structure. Can we make a pi bond there? Okay, we'll take a look at our carbon. That carbon would have too many bonds, so we have to break a pi bond. Do we have an extra pi bond? Yes. What is that going to do to the basicity of that nitrogen? More or less? Less basic, because I've taken those electrons and pushed them into the structure, preventing them from reacting with hydrogen. So I would predict A to be a stronger acid than B. Did I say that right? Oh, I meant base. Thank you. A stronger base. A is a stronger base than B. Okay. What about C? Is C a little bit trickier? Why? You're right, it is trickier. There's 2 nitrogens. So we have to evaluate both of those nitrogens to decide if they're basic or not. So what we'll try and do, just like every other process, is start resonance. Which one do you want to start with, left or right? Left. I like that answer. Let's go ahead and move those electrons in. How many bonds would this carbon now have? 5. So what happens? Got to break a pi bond. Do I have a pi bond to break? Yes. Okay, we could move those electrons out. What does that mean about the basicity of that nitrogen, our box nitrogen? More or less basic? Less basic because I'm pushing the electrons into the structure. I want them to come out of the structure. Okay, so we could say that nitrogen isn't very basic at all. We would probably rank it down towards B. Okay, what about the other nitrogen? We'll come back to that one in a second. Your statement, that is. I did hear you. Let's attempt resonance again. So let's move the electrons in. What happens? Too many bonds, what do? Break a pi bond. I do have a pi bond. Well, that wasn't very productive. Okay, so no resonance there. What about trying to push them the other direction? Same thing. No resonance there. So we might go through and say, well, that nitrogen is more acidic than our other one. So we could go through and say, this is our acidic nitrogen. And I'd agree, that is basic. Okay, it's not that difficult, right? It's basic. Let's see if that works. Okay. So if we take a look at C, we would probably then start to shift it up closer to A as far as base strength, because we now have a nitrogen, okay, that doesn't have resonance, just like in the case of A. Okay? But what were you saying, Paul? There was an extra thing to evaluate here. Maybe. What was that?
When you did the first one, the electrons moved into the other nitrogen, making it a negative.
What charge does that nitrogen become? Picks up an extra lone pair, formally negative. What do I want my base to have? Electrons, extra electrons. What did I just dump onto this nitrogen? A whole bunch of extra electrons. What does that mean about the base strength of this compound? It's going to go up. So we end up generating our strongest base. Hey, I got it right. Okay, with that last one. Okay? Kind of makes sense? So what we're trying to do is evaluate how resonance can affect the reactivity of our structures. Okay? If it can. Sometimes it just doesn't. That's what we saw in a lot of the alkyl halide reactions. Okay? Questions about base strength, particularly with nitrogens. Okay. So what we're going to go ahead and do now is move to just kind of the summary slide as far as our acid-base characteristics go. Okay. When we shift across the periodic table, that should say really HF, because that's a better option in this case. Why should it say HF and not HCl? Someone said the answer. I heard it, and it wasn't electronegativity. It's size. We look at the rest of those atoms, they're all the same size relatively. We don't want to throw in something else like HCl, which is going to mess up our ranking system here. Okay? So what we're trying to do is evaluate under each of those columns. Fluoride is the top of our halogens. Okay, oxygen. Anybody know what this one is? Good, because I'm guessing. I think it's a chalcogen. Uh-oh. I can't remember that. It's an oxygen group. What's the next one? I thought so. Hey, we caught on fast. Nitrogen group. And the last one, carbon group. Because your instructor is an idiot and can't remember them. Okay? Not like it was all that important anyway. But anything under those columns are going to react very, very similarly. Okay? So when we look at our halogens, they will only act as acids. Okay? They're either super electronegative or big, or ultimately both. Okay? So our halogens, as we move across, what is that, right to left across our periodic table, we'll only see those act as acids. We might also see them act as good leaving groups. When we move one column over, what do we end up seeing? What's the next group? The oxygens. Go figure. You'd think I actually planned it, right? Okay. When we move to the oxygens, we're now getting into our mixtures between acids and bases. Okay, so our alcohols can act as both an acid and as a base depending on the circumstance. We move one column further over. Now we move into nitrogens. We lose that acidity quality, and we move into nitrogens being primarily bases. Okay? We take one more step. We move into the carbon atoms. Hey, I started to remember them. The carbon atoms, and what happens as far as reactivity with our carbons, particularly carbon-hydrogen bonds? Virtually no reactivity. There's no difference in electronegativity. Size is negligible. We end up saying no real acid-base characteristics. Okay? And just for the sake of me kind of delaying time so that we didn't start substitution, I just happen to remember. I might be getting these backwards, but I think I'm right. It was chalcogens. No idea why, but that is the name. And the nitrogens are the nictogens. I don't know. That's what it is. Look it up. I'm right. It might be swapped, but those names are pretty close. I might spell wrong. You know that. Okay? Questions about acid-base characteristics? Okay. Please review some acid-base chemistry. Look at the results of these. If an oxygen acts as a base, if an oxygen acts as a base, what ends up happening? So let's take a look at our two lone pairs here. We got our carbon. Just draw that out, saying we got some bonds over there. If it acts as a base and it reacts with H+, what's the result? Thanks for all jumping in at once and answering that. You know, the dead air silence works great on YouTube. I like it. Okay. We get a positive charge on that oxygen, right? Does oxygen want to be positive? No. So what does it do? It wants to steal electrons. Where can it get electrons from? Could steal them from the hydrogen, in which case we go backwards back to our alcohol. Where else could it steal electrons? From the carbon. What happens to the carbon then? Our carbon becomes incredibly positive, which means our carbon becomes very electrophilic. Much the same as we saw in our substitution chemistry with our alkyl halides. So if we're going to try and do a substitution reaction, we're going to end up treating our alcohols with acids first, because that now activates that functional group to really wanting to get the heck out of there, so it stops being positive. So we can help facilitate a substitution reaction by activating the alcohol and turning it into a water group. Okay? So the acid-base chemistry that we're talking about today will show up on Wednesday when we look at our substitution chemistry. Okay? Take it a step further. What happens? Let's erase all. You didn't have any questions about that, right? That's good. I left it at the intermediate, so I didn't say where we could go from there. But yes, ultimately, water could leave. We'd have water and the carbocation. Okay, what happens if we react our alcohol with a strong base? For the sake of argument here, let's just say B for base, or why not? Waste some more time. Write it out as base. What happens? Now our alcohol is going to act as an acid. So we'll take the electrons from our base. Those will come up, steal the hydrogen off. What happens to the electrons between the oxygen and the hydrogen? They go to the oxygen. What's the result? Now when we look at our product, we get our carbon again. We've got our oxygen now with an extra lone pair, which means it is negatively charged. We would still have our base floating around. We could call that Hb+, just to be nice. Say it's there for balancing sake. What's special about that negatively charged oxygen? Has to do with it being negatively charged. Can act as a base. What else could it act as? Most importantly, it could act as a nucleophile in, say, maybe a substitution reaction. What kind of substitution reaction? SN1 or SN2? SN2 because it's negatively charged. It's a strong nucleophile. Okay? So if you remember all those substitution patterns, just to give you an idea, okay? So we'll clear everything off here. So you can see where we're starting tomorrow. Substitution reactions. Okay? So you're going to have to be familiar with all of those rules on why individual substitution reactions occurred and which mechanism, with now alcohols also being included into it. So we're going to start to compile and build upon the acid-base chemistry and characteristics of alcohols and now shift that into substitution reactions. Okay? So Wednesday, we're looking at acid-base, adding to substitution and elimination reactions. It's going to be both. Okay? Look at that.